Yes, very good morning, everyone. Welcome back.
Good morning, sir.
Good
Yes,
morning, sir.
Good
welcome.
morning,
Happy New
sir.
Year, sir.
Welcome back. Wish you all very happy New Year 2021.
Happy New Year, sir.
Happy New Year. Happy New Year, sir.
Thank you. Yes, any doubts from yesterday's class? Any doubts from yesterday's class?
No, sir.
Okay. So the last problem we did, hope you are clear about it. Yes.
Yes, sir.
Yes.
Yes,
Okay.
sir.
And electrical students might have observed this. I'll be doing most of the instrumentation problems, right?
Yes, sir.
The reason is instrumentation paper is having a good weightage, so more number of sample problems are there. Whereas in electrical, it is a less content. Okay, so some of the problems, okay, I'm taking from electrical gate paper as well. Okay, so if you cover the instrumentation papers, gate papers, you are done with the electrical paper, assuming you have a good weightage in 2021. Okay, or upcoming years. Okay.
Okay,
Okay,
sir.
sir.
So today we'll begin with the next topic. What is the topic I said yesterday?
For
That's class.
measuring AC, we are
Yes.
using PMMC.
Yes. Can I use PMMC to measure AC? Otherwise, take the challenge this way. Okay, as an instrumentation engineer, you are given a challenge. You have only PMMC, but you have to measure AC voltage. You have AC voltage, you have to measure it. That's a challenge. So during the interview, someone is giving you the challenge. So tell me how you will meet this challenge. That's a limitation we have. The instrument what we have is capable of reading DC only. In fact, with respect to the fundamental of the instrument is capable of reading only average. But whereas a pure sine wave or a pure square wave or pure triangular wave, which we call as instantaneous or AZ, okay, symmetric square, symmetric sine, symmetric triangular, all are going to give average of 0. But if you pass that AC signal to the instrument, definitely the instrument will read 0, no doubt about it. Okay, but by understanding the limitation of the PMMC instrument, how to measure the RMS value of the waveform or RMS value of the signal using PMMC. That's a challenge for us now. How to use PMMC for AC measurement. AC voltage or current measurement. Yes, anyone? AC. That's very important. So what we have is a PMMC instrument. Polarized. This is plus, this is minus. I have a PMMC. 0 to 1 milliamps instrument. The basic meter moment with meter resistance is equal to, for example, 10 ohms. That's a instrument I have. Okay, so with this instrument, okay, which can measure any average current or DC current up to 1 milliamps. That's the instrument I have. I can say it is DC responding or average responding. On the other hand, what I have is here an AC voltage that is having a range of 0 to 10 volt, 0 to 10 volt RMS. Because already we know the fundamental is given in electric circuit. Any AC voltage, its effective value is the one responsible for creating the power across the load. So therefore, by habit, we always AC means we measure the RMS value of the signal. So the input is in terms of RMS. Okay, what is RMS? If I say the waveform, this is a AC sine wave. So this is my V in of t in instantaneous with respect to time. Instantaneous signal V in of t. This signal can have any value between 0 to 10 volt RMS. So this signal V in of t will have a peak value, assuming it is symmetric sine wave, and will have a minus Vp. Will have a time period with respect to that it is having the frequency. Yes. Now tell me what's a VRMS of the pure AC sinusoidal signal.
VP by root 2.
VRMS of a pure AC sinusoidal signal is nothing but its root mean square value mathematically square your input, that's V in square of t into dt, then take the mean. So then go for the mean. This is your square representing the square of the signal, and this is mean, and then apply the root. That's what the mathematical meaning of RMS. You're all aware of, probably in signals and systems also, sir probably taught this signal RMS,
Yes.
correct? Yes, same thing. So that's a mathematical. A practical sense is already given in electric circuits. Okay, fine. So those who didn't attend electric circuit, probably, okay, we'll be going through this fundamental of why we have the habit of representing any AC source by its effective value or RMS value. So that's the input signal we are about to measure. On the other hand, what we have is only the PMMC instrument. Tell me how to achieve this or how to meet this challenge, how
Sir,
to achieve the goal.
we can square the input
We can
V
square the
naught.
input, then
Then the PMMC will measure the average value, that is mean
okay.
value.
If you go for the square of the signal, then automatically square of the signal will become positive.
Positive.
Yeah, yes, sir.
Square of the signal will become positive. All of you getting this point? All of you getting this?
Yes, sir. Yes, sir.
If you square the signal, then you can go for give that squared signal as the input to the PMMC, but the PMMC won't give you VRMS. Instead, according to you, it will read V square RMS. Getting Rahul? Why? You are squaring
Yes.
the signal, and then
Yes, sir.
automatically the instrument will take the average of it, correct?
Yes, sir.
Because instrument is going to respond somewhere, you're going to square the signal, assuming you're going to square the signal. So then you have a squaring mechanism. Assume you have a squarer. Then the signal is squared and available as what? V in square of t, correct? Then
Yes,
if you
sir.
pass that signal to the instrument, then tell me what you will get. You'll get the average of the squared signal. Then what is
Yes,
average
sir.
of the squared signal? V square RMS only. The instrument will respond for V square RMS. Therefore, theta will be proportional to V square RMS. Then the scale is going to become non-uniform. Okay, these are the problems. All of you getting?
Okay, sir. I
Understood?
thought, sir, after measuring V square RMS, we can
Yes.
calibrate accordingly, like taking square root like that.
Okay.
I
Okay.
thought like that.
So when you take the square root, then it will be mathematically square of the signal. Root of a signal is always either positive or negative.
Yes, sir. Yes, sir.
Then mathematically we'll be in trouble. Okay.
Yes, sir. Yes.
Then we need to go for the absolute. Then
Yes, sir.
absolute of your square you need to go for. Correct.
Yes, sir. Yes, sir.
Okay. Then the big problem is who will square your signal? Tell me. Who will square your signal? Who will give the squared version of your AC waveform? Nobody will give. We don't have any circuit which will square your input and give it as output. Can you name any circuit you studied in the past? 1 minute. Okay. Yes. Fine. Can you name any circuit which you studied in the past which will square the input and pass it as output?
The amplifiers we can't decide accordingly.
Amplifier. Okay, you can go for an analog op-amp circuit which will square and pass the signal. Correct? Yes. Yes, Nirmala.
Yes, sir. Is it possible, sir?
Okay, but anyway, I already said squaring, okay, will be done. But after that, even though you are doing squaring, then you need to take the root and pass the signal to the, okay, you need a squaring circuit and root absolute. So you need to square your signal and pass it to the root and then take the absolute of it. Then you can get the, okay, average of it. Then there is a possibility of reading VRMS. Correct? All of you?
Yes, sir.
So we are thinking in the mathematical route because I said VRMS. Okay.
Yes, sir.
Okay. So the better route of squaring block is not available for us. Instead, the instrument is capable of reading only the average. The instrument is capable of reading only what? Average. So try to convert this AC signal a pulsating DC. Who will give pulsating DC?
Rectifier, sir.
Yes,
Capacitor.
yes,
Uh, okay.
yes, rectifiers. Yes, you need a rectifier as a block. We are familiar with the rectifiers. So have rectifiers. It can be off wave rectifier or it can be a full wave rectifier. So if it is a rectifier, then you get a pulsating DC. Either if it is off wave rectifier, you will get it like this. If it is a full wave rectifier, you will get it like this. Getting? Yes or no?
Yes, sir.
Then you can pass the signal happily to the what? PMMC, which is going to get the average of this signal or average of the signal. Hope you remember, if it is off wave rectifier, what is the average of the signal? Average of the signal, Vp by pi. Hope you remember. If it is a full wave rectifier, yes,
VP
what's
by
average? V average will become 2
V
Vp by
2
pi.
VP.
So the
OVM.
instrument will respond for this. This is very easy. You don't need a squarer. You don't need a block for getting the root of it. Rectifiers. Because of a rectifier, if you take, it demands only one diode. With that, you can accomplish an off a rectifier. Getting everyone? Getting everyone?
Yes, sir.
Yes,
Okay,
sir.
Yes, sir.
easily. Yes, what is the only extra element you need is only a diode. With that diode, you can convert a pure AC into pulsating DC. That pulsating DC can be given as an input to the PMC instrument. Then PMC instrument happily responds for this average. But anyway, your V average is proportional to what? VP. Is the point is clear? V average is proportional to VP. And VP is what? VP is what? We know VRMS. What is VRMS? VP by root 2. Correct? For a pure sine wave, VP by root 2. So what is VP? VP is root 2 times what? VRMS. All of you getting this point? Otherwise, shortly I will say VP is proportional to VP is proportional to VRMS, whereas V average is proportional to what? VP. Therefore, theta of the instrument is proportional to what? V average, assuming it's a PMC voltmeter. Then theta is proportional to V average means automatically V average is proportional to VRMS. Directly I can say, okay, so the proportionality constants are there. V average will be because VRMS influences VP, VP influences V average. Therefore, theta is getting influenced by V average. Therefore, it is possible to get the deflection proportional to the parameter to be measured. The calibration constants are there in the picture. Getting everyone? Following this?
Yes, sir.
Getting Rahul? Getting Deepthi?
Yes, sir.
Okay, so that's a way. That's idea. So it's possible to get uniform deflection once again because theta is going to be proportional to RMS. Okay, some proportionality constant will be there. We'll see that. Okay, so these instruments. So when you have a PMMC in your hand, happily you can take one diode from the laboratory, convert your entire setup ready for measuring an AC signal by using a single extra diode. So we call them as rectifier instruments. We call them as rectifier instruments. A rectifier instrument uses PMMC only. Rectifier instruments are capable of reading AC. Okay, but AC we are measuring only by using what? DC. In between rectifier is the interface between your input to be measured, which is AC, but the meter demands average, that should be a DC. Okay, right? So this is here you're demanding DC, but the input is what? AC. So how to convert the AC into pulsating DC? With that, the instrument will happily respond. Therefore, you need a simple rectifier. It can be a half wave rectifier or it can be full wave rectifier design. Okay, we call them in general rectifier instruments. What's the beauty of rectifier instruments? Rectifier instrument uses PMMC, and PMMC known for PMMC known for
Average.
PMMC known for very uniform scale. PMMC known for very uniform deflection. Because of that only you get very uniform scale. That's a benefit of using PMMC. None of the other AC instruments will give uniform scale. Example, moving iron. We'll talk about this little later. Moving iron, if you take it is the worst scale it is going to have, because in the inputs beginning side, zero scale deflection side, the scale will be crowded, whereas the scale will be crowded, closely populated readings around zero scale deflection. Around full scale deflection, it is going to have expanded scale, such a ununiform or non-uniform scale it is going to have expanded. So none of the other AC instruments will give you such a uniform scale. That's the purpose of going with rectifier instruments. The beauty of PMMC, it is offering uniform deflection for the average it is sensing. Why can't we exploit that uniform scale even for AC? Because the other AC instruments fail to offer such a uniform scale. If you want uniform scale measurement, it has to be done only by using rectifier instruments, where the indicating instrument is again the PMMC. Are you getting the point?
Sir,
Yes, sir.
Okay. Any doubts till
the
now?
PMMC is termed as rectifier instrument, sir.
No. PMMC is by default average responding instrument. Okay.
Rectifier instruments, it uses PMMC.
PMMC, yes.
Okay, sir.
Rectifier instrument uses always PMMC as a readout device.
Okay, sir.
Okay. What rectifier is doing? Converting your AC into pulsating DC. That's all. Rectifier instrument is fundamentally it's an AC instrument. Rectifier instrument means it's an AC instrument, measuring AC only. It can measure DC also, not an issue. You can give the input as DC or AC, not an issue. Okay, it will respond. But calibration will be different for DC and AC. All of you getting? Understand?
Yes, sir.
Okay. So you are making it only for AC. Okay, it is capable of sensing DC. Since your calibration is going to be different, okay, we'll see how it is going to differ, okay, for DC and AC, the calibration. But anyway, rectifier instrument means I should not supposed to measure a DC quantity using rectifier. You need to measure only the AC quantity. Okay, that's a rule of thumb. Okay. If it is a DC quantity, directly you can use a normal PMMC voltmeter and PMMC ammeters, correct? It can be a DC current or DC voltage. You can go with them. Only when it is AC, you need a special interface, that is your rectifier, maybe half wave rectifier or full wave rectifier. All of you clear about this?
Yes, sir.
Yes.
Yes, sir.
So let us begin with the first rectifier instrument, that's by using half wave rectifier. Okay. So what is your PMMC voltmeter? Before getting into that, what is your PMMC voltmeter? What are the elements in the PMMC voltmeter? DC. I'm talking about DC PMMC voltmeter. What are the elements you have? A PMMC voltmeter is an ammeter converted into voltmeter. What do you have there?
Swamping resistor and
No, swamping is much before. Okay. Series resistance, multiplier resistance, you should call that.
okay.
Correct, Rahul? You have a
Yes.
series resistance R series in series with the meter. Correct? All of you
Yes,
getting?
sir.
Yes, sir.
Yes, sir.
When you convert an ammeter into voltmeter, you have a series resistance to bypass extra voltage, because the instrument, okay, is going to have less. What is the voltage you can pass across the instrument? What is the instrument given taken now? 1 milliamps
0
full
to 1.
scale with a resistance of what? 10 ohm. Instrument cannot have a voltage more than 10 millivolt. Okay. Therefore, rest of the voltage has to be bypassed only across the series element. All of you getting?
Yes, sir.
Okay, so therefore, a PMMC voltmeter is going to have two elements. One is R series, another one is what? The instrument, PMMC ammeter. Along with that, consider a diode. Along with that, consider a diode. That's all. Okay, so this is your PMMC voltmeter structure. It is having R series. Along with that, the instrument. That's a PMMC DC voltmeter. Okay, so here you have 0 to VFSD. Okay, here you have plus minus. This is 0 to what? IFSD, having the meter resistance RM. At full scale deflection, what is the current through the instrument? IFSD is the current through the instrument, and the instrument will have a drop of only IFSD into RM. IFSD into RM. Rest of the voltage should be falling across your R series. Okay. All of you getting? Otherwise, you take this as your meter voltage. So this is the meter voltage. So when the current through the meter is varying between 0 to Im, varies between 0 to IFSD, okay, and voltage across instrument, okay, you can take it as, you take this as 0 to V, you are measuring, okay, right? 0 to V you are measuring, and the voltmeter voltage will be what? 0 to VFSD. I'm talking about DC ammeter voltage at full scale. This is, you take it as VFSD when the current is IFSD. Then you are extending the meter range from VFSD to what? V. Then automatically you will get M. That's a root. V by VFSD is your M. Therefore, R series will be M into, sorry, M minus 1 into what? RM will be the calculation. Correct? Getting everyone?
Yes, sir.
Following this, everyone?
Yes, sir.
Okay. So that setup only we are going to use. Along with that, we are going to have one extra resistance. That's all. Sorry, extra element, that is diode. Yes, getting everyone?
So 1 minute the previous slides.
Yes. Yes, Monopriya. Dhanvasha, right?
Oh yes, sir.
Yes, Dhanvasha. Any
So
doubts on this?
yes, sir. Why we have cancelled the VM and the road VFST?
VM? No, I took it as VFSD. Because earlier I took here as VFSD. Because I took IFSD for the instrument, take that as a VFSD as well.
We are
Okay?
measuring 0 to VFST only, no, sir.
0 to V. 0 to V. Instrument range is 0 to VFSD. I took it as a voltmeter. Okay? Because it's an ammeter, Dhanvasha,
sir. Okay,
it can
sir.
measure 0 to IFSD. Instead of that perception, I'm assuming it is a voltmeter which can read 0 to VFSD. Then easily you can feel this ammeter as a voltmeter. Then go for voltmeter extension.
Okay, sir.
With that, you can play with M. Okay?
Yes, sir.
It's my perception, that's all.
Okay, sir.
The idea is this. So, full scale deflection of the instrument is 10 milliamps. What is the RM? 10 ohms. Let me take. So, tell me what will be the voltage across the instrument. VM will be between 0 to 10 millivolt. That's all. Correct? Yes or no? 10
Yes, sir.
milliamps or 1 milliamps? 1 milliamps, so 0 to 10 millivolt. So therefore, I am perceiving the PMC ammeter as a voltmeter. So what is the maximum? 10 millivolt. So now I am going for example, 0 to 1 volt. Assume I'm going for 0 to 1 volt voltmeter. How much you need to bypass? 10 millivolt across your instrument. What is the remaining? 990 millivolt you need to bypass. What is the maximum current? 1 milliamp. So what's your R series then? R series is 990 millivolt divided by 1 milliamps. What do you get then? 990 ohm. Instead of that, I'm going with the equation Rm is equal to R series into, sorry, R series is equal to Rm into M minus 1. Tell me what is your M now?
1 by
1 by 1 by
100, sir.
Rm is 10 ohm, right? What is M? M is equal to 1 volt divided by 10 millivolt. Then what do you get? 100 you get. Correct?
Yes, sir.
Then M is equal to 1 by 10, 100. Fine then. Rm is equal to 10. So 10 ohm into, what do you get then?
99.
99 minus 1. What is it? Sorry? 100 minus 1. What is that then?
990.
Into 99. What do you get then?
990 ohms.
Same?
Yes, sir.
That's all. Okay, so it's a perception. All of you getting this?
Yes, sir.
Yes, sir.
It's up to you finally. Okay. You can perceive an ammeter also as a voltmeter based on the voltage across it when the current varies from 0 to IFSD. Okay.
Yes, sir.
So we'll begin with the first rectifier instrument. Rectifier based PMMC instrument, let me call. So we have an ideal diode. Then this structure is same as the previous structure. This is your DC voltmeter. Along with that, I considered this diode. That's an interface. Here it is going to be a DC, and this is going to be what? AC. In between, I have this element that is going to be doing off wave rectification. That's all. Understood, everyone? This is the extra block. You need to connect it. Okay. If you are about to measure AC. Getting everyone?
Yes, sir.
So now let me focus on assuming the input voltage, okay, varies between A0 to VFST. It's RMS. This is by default RMS voltage. Okay, 0 to VFST. So then assume it is a 0 to 1 volt AC voltmeter or 0 to 10 volt AC voltmeter I'm building. I want to measure 0 to 10 volt RMS. Okay, so what can be the maximum voltage? When the input RMS varies, the peak also going to vary, correct? So therefore, what will be the peak then? Peak will be, let me call this as Vin. This is Vin. By default, Vin is RMS. Vn can be an RMS value between 0 to 10. So what is Vp then in terms of Vn? I'm calling this as Vn, that's RMS voltage. Yes, what is Vp? Peak voltage. Vn is RMS. What is the peak? Root 2 times your RMS, correct? Yes or no?
Yes, sir.
Then Vp will be equal to root 2 times your, okay, so maximum, let me make it at full scale. So this will become like 10 volt. So that will be the Vp. What is that? 10 into root 2 volt will be the maximum. So the plan is you are getting a peak of, I'm setting at full scale deflection. So you're getting 10 into root 2 as a voltage. Then this is passing through the ideal diode. So tell me what will be this potential. Let me call this potential as Vx of t. Can you plot Vx of t now? What will be Vx of t with respect to time? This diode will conduct only during positive off cycle, and it won't conduct during what? Negative off cycle. Are you getting?
Yes, sir.
Yes, sir.
So diode in forward bias during positive off cycles. Diode is in reverse bias during what? Negative off cycle. Therefore, during negative off cycle, diode is open circuit. During positive off cycle, diode is short circuit. If that is the case, tell me what's the potential you will get across these points. This point, it is always AC, correct? Input is always AC. The current is existing through the diode only during positive off cycle. So let me talk about what is Vx of t. Vx of t is the instantaneous voltage with respect to time between your R series and the PMMC ammeter. So this is going to be a pulsating DC. Getting all of you? Yes or no?
Yes, sir.
Yes, sir.
So that is going to have a maximum of what? Vp. So then this is the input. Instead of giving a DC signal for this, okay, DC voltmeter, this is a DC voltmeter. This is your DC voltmeter. Instead of giving a DC signal, you are giving a pulsating DC, means definitely the instrument will respond or not. Average is there. A finite average is there. Definitely the instrument pointer will deflect for this average because theta of the PMC is proportional to the average. Agree everyone? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So it is going to respond for this average. We'll exploit this fundamental, we'll make a design. So it's your call. Either you can focus on voltage across this, otherwise you can also focus on current through the PMMC of T. You can also focus on current through the PMMC. So what is the peak voltage Vx of T? You know what is the peak? Vp. So tell me what will be the current, and this is your meter resistance, and this is your R series. At this point, it is a maximum of Vp. So tell me what is the maximum current? Instantaneous current through the PMMC. You can say I PMMC of T, because once you know the instantaneous current exiting the moving coil, then you can go for the average of this current. Then you know what will be the reading of the instrument. So it is better to go for the instantaneous current exiting the moving coil of the PMMC. Then what will be the current? It is also going to be pulsating. Agree everyone? Yes. It is going to have a peak value of IP. So what is IP then? We know IP is equal to the peak voltage is Vp. The peak voltage Vp, that is falling across R series and what? Rm. Therefore IP I can write it as Vp divided by R series plus RM. Getting everyone? Yes or no?
Yes, sir.
Everyone following this?
Yes, sir.
Yes, sir.
Then I can go for the instrument reading as the average of this. What is the I average? That's a reading of the instrument. That's your meter current. Average meter current. That is what it is going to read. So what's average? Of a rectified average, it is going to be IP by pi. So take this as, it's a constant peak current. So take it as IP. So capital letter can be used because it is not, the peak current is not varying. Peak current is constant. Okay, it's a constant value. Then I average, that's a reading, current reading of the instrument, that is equal to the peak current exciting the moving coil divided by pi will be the average deflection of the pointer, which is calibrated in terms of the current already. Getting everyone? Following, all of you following this?
Yes, sir.
Yes, sir.
Okay, now we'll go for the design. That's a basic principle of an off-wave rectifier PMMC instrument. Off-wave rectifier PMMC instrument. Okay, we'll make a design now. Okay, we'll see how to make the design. So design at full scale deflection. Input is 0 to 10 volt. So V in is 10 volt. V in is 10 volt RMS. V in is 10 volt RMS. This is going to be AC sinusoidal signal. What is the peak value? You know that. That's V in of T. I said when I say V in, you talk about only RMS. If I say V in of T, yes, represent in terms of peak. What is the peak? 10 into root 2 volt. Getting everyone? Yes. Yes or
Yes,
no?
sir.
Now let me focus on the current through the moving coil shortly of T, instantaneous current. Now tell me when the diode conducts. Diode is on during forward bias. That is during positive off cycles only. Diode is off during reverse bias. That is in every negative off cycle. Correct? Of input. Every positive off cycle of input, diode is on. Every negative off cycle of input, diode is off. That means the current is existing only during positive off cycle. No current during negative off cycle. Correct? Therefore, IMC existing during positive off cycle, whereas I moving coil is equal to 0 during negative off cycles. Getting? Yes or no? Following this, all of you following this.
Yes, sir.
Now, problem is at full scale. Okay, so now let me, at full scale, the input is 10 volt. Now let me make the analysis at pi by 2. At pi by 2, at theta equal to pi by 2. What is the current at theta equal to pi by 2? What is the voltage at theta equal to pi by 2? Refer the instantaneous waveform V in.
10
What is the
root,
voltage at theta equal to pi by 2?
10 root 2.
At theta equal to pi by 2, the input voltage is what? Peak value, correct? Input is at its peak. So then take, that is the input. Okay, this is a peak value. What is the VP? VP is equal to 10 into root 2. And diode is in forward bias. Okay, so no drop across it. Assuming ideal diode. Then 10 by root 2 is the voltage here. Therefore, if you plot I moving coil current, then the maximum current is this. That's a maximum current. So again, you will get this instantaneous waveform during the next cycle. So yes, what is the maximum current for this I moving coil of the PMMC? You can say I PMMC or simply I moving
1
coil.
milliamp.
What is the current? What is the current? No, I'm not referring the instrument full scale. Anyway, it has to be. The instrument current has to be, because when you are giving input full voltage, when you are giving input full voltage, the current should be what? Full. All of you getting? As of now, I am not referring the instrument, I am referring the circuit. Okay, so tell me what will be the moving coil current. It is your, as I given, already given, right? The
Yes, sir.
point is
10
already
root
made,
2
right? What
by
is that? VP divided by peak current, you tell me. What is the peak current? VP by R series plus RM. R series not yet known. All of you getting? All of you getting this?
Yes, sir.
Okay. Now, okay, so there are many ways you can also play with the average voltage here, but let me go with the instantaneous moving coil current. That's a better route, in fact. Okay, even though two steps are higher in this route, better, that's a better route. So always find out what is the instantaneous current exciting the moving coil. Then with that, you go for the average. The goal is we are making the design. Design means we need to find out R series. We need to find out R series. So what is the value of R series needed? What is the design here means? What is the value of R series needed? When the input is 10 volt RMS, the current through the instrument is 1 milliamps. All of you following? All of you following? When the input is 10 volt RMS,
Yes,
I need
sir.
to choose my R series in such a way that the meter is at full scale. Therefore, I will calibrate 1 milliamps later into 10 volt reading. 10 volt what reading? RMS reading. All of you following me?
Yes, sir.
Yes, sir.
Because I am designing in such a way that when the input is 10 volt RMS, it is going to produce input is full scale. Let the meter is also deflecting for the full scale. Then I will do a simple calibration of 1 milliamps into 10 volt RMS. Therefore, now we are giving already a full voltage. That full voltage is giving such a peak current. Then with this, I need to make my average current is equal to 1 milliamp. So with this, I need to make my average current now to create full scale current. My average current should be equal to what? IFSD. Following everyone? When Vn is VFSD, I average must be equal to IFSD. Then only the meter will deflect full. Following Rahul?
Yes, sir. Oh,
Now what is I average? Tell me what is I average?
Sir,
Yes, Monopriya.
sir, here I mean V in is equal to VFST we're taking now, sir.
Vn is?
When V in is VFST, I average is IFST.
Yes, I average should be equal to IFSD.
This VFST is 10 root 2 or the 10 VRMS voltage, sir.
Vn is VFSD means that is 10 volt RMS. Getting that,
Okay, sir.
Varsha?
Okay, sir. Not the 10 root 2.
10 root 2 is your VP.
Okay, sir.
That is already given IPS in terms of what? VP, correct?
Okay, sir.
Following that, Varsha?
Yes, sir. Following, sir.
So now the point is very simple. When Vn is 10 volt RMS, the peak voltage is 10 into what? Root 2 volt. With this, I need to produce the full scale average deflection. That should be equal to what? 1 milliamps. So that should be my meter current. When input is 10 volt RMS, meter current should be equal to the full scale deflection current. That is average. Okay, so this is the instantaneous voltage exciting the moving coil. That is resulting in instantaneous current. That is resulting in I average. And we calculated I average now. I average is equal to, for half wave rectified signal, IP by what? Pi. What is IP? IP is VP divided by R series plus R meter. All of you getting?
Yes.
Divided by pi. And that should be equal to 1 milliamps. And what are the knowns? VP is known. VP is well known. What is the only unknown?
RS.
RS, R series, correct? VP is known, R meter is known, pi is known. Then what only unknown is R series. That's your design. So complete the design now. We'll verify how it is working later. So now design is to find a suitable value for R series so that when the input is full scale, the instrument reads full scale. That's your design. Okay. Yes. Now from this, I can write this as VP divided by pi into R series plus what? RM. That is equal to the full scale current, IFST. Understood? Theoretically, let me give the expression first. All of you getting?
Yes.
Okay. We can also substitute number later. That's a expression to remember. IFSD is the I average. So this is your current, okay, making the average current. This is your I average. I average must be equal to IFSD. Now what's only unknown? R series. Then I can write this as VP divided by pi into IFSD is equal to R series plus RM. Agree everyone?
Yes.
That's a total meter resistance needed. Okay. In fact, that's a total meter resistance. All of you getting this point? Tell me what's the total resistance from here? That's a total resistance. R series plus R meter. So first calculate this R series plus R meter. But remember, you're not playing with the DC voltage and DC current. You're playing with the pulsating DC and the pulsating current. Okay. So then yes, you can calculate this now. So then R series plus RM substitute. Get it now? It is 10 root 2 divided by pi into 1 milliamps. Tell me what's the number? Calculate the number. Yes, one step to complete the design. Pi into 1 milliamps. Pi milliamps you can say. It is voltage. 10 root 2 voltage. Volt per amps. It is going to be in ohms. Get that in kilo ohms. Otherwise get that in ohms.
4.5 kilo ohms.
10 root 2 divided by pi kilo ohm. So I should say this as 10 root 2 by pi kilo ohms. That's a number. Yes.
4.5 kilo ohms.
Yes. Few more digits I need, Rahul.
4.50158.
1,
58.
1, 6. Let me take kilo ohms. Okay. Yes. Now tell me what is our series. Therefore, R series. That's completion of your design. Here subtract RM from the overall value. In terms of ohms, Rahul, 4501.6.
Kilo ohms. Sir. Yes, sir. In terms, yeah.
Okay. Lose RM. RM is just 10 ohms. Discard RM. This is your R
4,
total. It is 10 root 2 by pi kilo ohms. Remember, I'll be using this later. Okay. Yes, R series, please, finally.
4491.6.
4491.6 ohm will do it. Okay, will serve the purpose of converting this, okay, instrument into an AC voltmeter. Okay. Getting all of you?
Yes, sir.
So design is over. Tell me what is R series? Verification. We'll do a simple verification. Whether it is working fine or not. Yes, what is R series you have taken? 4491.6, correct?
Yes, sir.
Any other digits you want to say after 6?
It is actually 581 like that.
581, na? Give me
Yes,
the
sir.
exact digits so that there
4
won't be any fault later.
4491.5815.
5815,
Yes, sir.
yes, Dhanvasha?
Sir, that R series, I approximated it itself.
Yes, instead of approximation, give me 2 more digits. Instead of this 0.6, give me what is the number. So this is your total. From this, discard 10 ohm. Tell me what you get. 4491.8.
58158.
158.
Yes, sir.
Then you make it. Okay. So maintaining such an accuracy so that we won't commit any mistake. So tell me what is the number here. 0.5816. Even you can take 0.6, not an issue now. Your meter resistance is 10 ohm. And this is 4491.6. I want to verify now. How to verify? My input range is 0 to 10 volt. The 10 volt has created the full scale deflection. All of you getting the point? 10 volt. I'm checking the uniformity now. How uniform your deflection is, I'll tell you now. 10 volt is creating 1 milliamps means 10 volt RMS creating 1 milliamps means 5 volt RMS should create what?
0.5.
Yes. When the input is, all of you getting this point? When input is off scale deflection, then the deflection of the instrument should be off scale. which you won't get in any AC instrument. If it has 0 to 100 volt moving an instrument, 100 volt will be the full scale, but 50 volt won't give you the off scale. That's problem is non-uniform scale in moving ion instruments. Okay, even electrodynamometer, voltmeter also will suffer the same way. Whereas the only instrument which will give off-scale deflection in the readout device for the input off-scale deflection is only the rectifier type instrument. Remember that. So this is our expectation for the uniformity or linearity. Okay, all of you getting this point? I'm just making a linear interpolation. This is possible only when this entire setup is linear. So now I'm checking whether it is linear or not. Let your Vn is equal to 5 volt RMS. Vn is equal to 5 volt RMS. All of you getting? Yes or no?
Yes, sir.
Then tell me what's a peak current going through this. Peak current going through this. That is going to happen if you go for the current waveform. This is a current waveform. I of t. This is your I of t in the circuit. I of t is going to exist only during positive off cycle. No current in the negative off cycle. I'm taking the current. Instead of this voltage and this voltage, let me go with the current. So current is going to exist only during positive off cycle. So what is the peak current of it? That is the current going through the instrument also. That's a meter current as well. Okay, I of t is equal to the meter current. Yes. Now tell me what the peak current, IP. You know VP. Set the problem once again at theta equal to pi by 2. At theta equal to pi by 2, you will get input is equal to peak. What is the peak? Peak value of the input? Input RMS is 5 volt. What's the peak value? VP is equal to 5 into root 2 volts. But by mistake, sometimes 5 by root 2 also we will write. Apply caution. Okay. RMS is VP by root 2. Remember that equation, and from that begin. Yes, begin. It takes hardly a few seconds to write this equation. What is RMS? Write the connection between RMS and VP. VP by root 2. If you commit a mistake here, no one will help us. Ready? Yes or no? So VP is 5 root 2. Tell me what is IP now. You know the entire resistance in the circuit. Diode is an on condition. It is a short. Tell me what is the maximum current. So that is 5 root 2 divided by total resistance. Correct? What is the total resistance? 4491.6 plus 10. So what do you get then? 5501.6 ohms. All of you getting?
Yes, sir.
Yes. Tell me what is the current in milliamps, please.
1.5707 milliamps.
1.5707 milliamps. Remember? Okay. So I have approximated the R series. Okay. So I'm not taking the accurate value. So all are approximate now. And again, you're going for the approximation, rounding of this data. That's your peak current. All of you getting this peak current? Yes.
Yes, sir.
Yes, sir.
Now, if this is the peak current, your instrument, so what is the current exciting your moving coil? Your PMMC current is this. I PMMC of T is having a peak current of this means. So tell me the instrument reading is only its average. So the peak current is this IP. So tell me what's a reading of the instrument.
Sir?
Reading of the instrument is Monopriya.
Sir, 5 rooted by 4501.6.
45R. Yes, sorry. Okay, please correct it. Correct Monopriya. Dhanvarsha, please check.
Oh, sir, I took it correctly only, sir.
Okay then.
It
Yes,
directly added the
1.5.
Okay. Are you getting, all of you getting this?
Yes, sir.
Same number, right?
Yes.
I committed a mistake. Okay. So it's 4501, not 5501. Okay. Anyway, that's why I need to verify here. Okay. Usually in the calculation, I'll go with this 10 root 2 by pi minus 10. Okay. So that there won't be any mistake in the verification. Yes, that's a current. Everyone agree with this?
Yes.
Yes or no?
Yes,
Yes,
sir.
sir.
Then tell me what is the meter current. The meter is going to respond only for its average, correct? So what's the meter current? Average of the instantaneous waveform that is going through the current going through the PMMC moving coil. Yes, what's average? IP by pi. So IP by pi 1.5707 milliamps divided by pi is your reading of the instrument. Hope it is 0.5.
0.4999.
Okay, 1 minute. 0 point. What is the data? 0 point
4999 milliamps.
4999. What is that 0 0.4999?
It's 5.5.
Then that is expected, right?
Yes, sir.
Then tell me whether your instrument is working fine.
Yes, sir.
All of you. Your
Yes, sir.
input is off
Yes,
scale.
sir.
The deflection is also what? As expected, off scale. Then if you give 2.5 volt, then you know what the response will be. If you give 2.5 volt RMS, then the meter will give quarter scale deflection. Off scale is a quarter scale deflection. It will give what? 0.25 milliamps. Then you can also give 7.5 volt RMS. It will give 0.75 milliamps. Linear? Linear?
Yes, sir.
Uniform deflection?
Yes, sir.
Yes. Okay. So try to create full scale. Then design at full scale. Verification at off scale is enough to confirm the uniformity of your deflection of the pointer over the scale. So that's how an off-air rectifier instrument has to be designed. Okay. And verified. Any design should be followed by verification. Yes, Rahul?
Sir, I have a doubt, sir.
Yes, Rahul.
This peak current is created, right? 1.57.
Yes.
That won't go through the meter,
That is going through the meter.
so it will damage the meter, right?
How the meter will get damaged?
Like how it is.
This is your instrument, Rahul.
Yes, I have a doubt, sir.
Accordingly, you need to make the coil. That's what it means. So the meters, it is responding only for what is I average. The meters already we said. What is the full scale deflection of the pointer?
1
Because
million.
actually your pointer is going to deflect this way, Rahul. Correct? This is your moving coil current. That's what I say.
Yes, sir.
Okay. Moving coil current. The moving coil is excited like this. Okay, so earlier what we discussed is only the current through the instrument should not be more than the full scale. Correct? What current we discussed? Average current only we discussed. The current which is producing full scale deflection, the instrument current, okay, should not deflect your pointer more than full scale. That's a point there.
Yes, sir.
Now also the pointer is not creating deflection more than full scale. But instantaneous current through the moving coil is greater than full scale. That's what you are talking about now.
Yes, sir.
Correct?
What happens at
This
that?
is happening only at off scale. Imagine at full scale. At full scale, what is your current? What is the peak at full scale? Now, what is the peak? 5 root 2. And what is your peak at full scale? 10 root 2. What will happen? This current will become double.
Yes, sir.
At full scale, what is that? 3.14 something you will get. Correct?
Yes, sir.
Yes, that is a current going through the moving coil. But problem is it won't damage your instrument, because when the instrument will get damaged, if the pointer deflects more than full scale. Correct?
Okay, sir.
Now will the pointer deflect more than full scale? It is it is becoming 3.4114, right? Sorry,
Yes.
1414. 3.1414. Correct?
Yes, sir. Something.
3.1414 milliamps you will get. That will be divided by pi, will give you 1 milliamps exactly as the average. Getting Rahul?
Okay, sir.
This is when VP is 10 root 2. This is your peak current, and this peak current is going to make I average is equal to exactly. This is 3.1414 is a pi milliamps current. It is pi
Yes, sir.
milliamps divided by pi. Pi will get cancelled. You will get exactly what? 1 milliamps. Okay. That's a good point for everyone. Okay, so the instantaneous current is greater than your full scale deflection current. But the full scale deflection current, what we talk about is the average current. So therefore, even though the signal, the current passing through the moving coil is instantaneous, the instantaneous current can be greater than your full scale value. Full scale value is 1 milliamps, but the instantaneous current can be 3 milliamps or 10 milliamps, but it's not an issue. Finally, the net average is more or less. At full scale, the net average should not be more than the full scale. Are you getting everyone?
Sir, so the PMMC rating 0 to 1 milliamps, that means the rating is given in terms of average.
It is reading, deflection. It is a scale deflection, pointer deflection only given.
That 1 milliamps corresponds to the average.
Yes, yes, that's average current only.
Okay, sir.
So
For
this
average
itself is
current,
average current. Okay, so you have to go to the PMC instrument. What is the PMC instrument data? What is the PMC instrument data? Theta average is equal to NBA by K into what? I average. This I average only 0 to 1 milliamps. We are not violating anything.
So it won't take the peak current, it will take only average current.
Yes, because it's already we proved.
Yes,
So
sir.
what is our
Okay.
deflecting torque? Theta of T, TD of T, NBA into what? I of T. What is I of
Yes,
T? That's a PMMC instantaneous current.
Yes, sir.
Already we played with this. Then we went for the average deflecting torque. What is that? 1 by T, 0 to T. Remember,
Okay, sir.
NBA into what? I of
I of
T.
T.
Then from this only we got average deflecting torque. That is the one responsible to produce average deflection theta. What is that? TD, NBA into NBA into what? 1 by T, 0 to T, what? I of T into DT. Correct? What is this? There itself we played with I average only. Understood
Yes,
everyone?
sir. Yes, sir.
Then yes, you forget that, all of you forget that fundamental. That's why the doubt comes now. Understood? All of you getting?
Yes, sir. So one more doubt, sir.
Yes. Well, let
Uh,
me check whether everyone is convinced.
yeah, okay, sir.
it
Yes,
seems
Dhanvarsha.
current flowing through that.
Yes, sir. Comment, sir.
That's why
Yes, Nirmala. Nirmala.
seems like IP pre-current is going through the instrument like that.
But that's not an issue.
Yes,
Because finally, what is making the deflection? What is making the deflection of the pointer?
I average.
Average, that's all. Already we consider this instantaneous thing in the first class itself.
Yes,
Yes,
sir.
Rahul.
We consider all these things. Yes, sir.
Yes, we consider all. Okay, so there should not be a doubt in that. That's why don't play with the voltage, better play with the current. Okay,
Okay, sir.
understood?
So
Yes.
also if only if I average is greater than the full scale, only then the pointer will
Then
deflect
the
more and
pointer will
will
deflect more than full scale, the damage for the moving assembly.
So as long as it lies, the average lies within the range of full
Up to
scale.
full
no
scale,
problem.
no issue for the instrument.
Okay, okay.
The safety of the instrument is well guaranteed if the average current going through the moving coil doesn't exceed your full scale deflection. That's a point for everyone. Understood?
Yes, sir.
Yes, Rahul, you thought of
Yes, sir.
one more doubt.
Yes, sir. One, I can't imagine how it is getting stabilized reading.
Then this is that's once again you have to go here only.
Again, that one. Yes, sir.
Yes, because where the TD of T, I of T, instantaneous current making instantaneous deflecting torque, Rahul.
Yes, sir.
Instantaneous current is making deflecting torque is also going to be like this. Your deflecting torque,
Yes, sir.
instantaneous deflecting torque is also going to be pulsating.
Yes, sir.
But who is making because it's a mechanical system, it is having moment of inertia, all those things, correct?
Yeah, okay,
Therefore,
sir.
finally, the response is only for TD average. The moment I say TD, that is TD average.
Yes,
So
sir.
average deflecting torque acting on the moving assembly responsible for your theta average. Understood?
Yes, sir.
Deflection average.
Yes, sir.
These
There was a
things.
period of zero, right? That's why I got
Yes,
confused.
yes, it's periodic, correct? Because the
Yes.
torque becomes, if that is the case, what has to happen? So your meter pointer should go from 0 to that 3.14 milliamps at full scale and then come back to 0. Again, it is 0 for 0 to pi and pi to 2 pi. Pi to 2 pi, no reading of the instrument.
Yes, sir.
0 to pi, it is following the cycle means. What will happen to the pointer? Then this is your scale and assume this is your 3.14 milliamps. What will happen? The pointer will deflect from 0 to 3.14 in 0 to pi by 2 will come back to 0, will stay there, okay, for negative off cycle, and again it will deflect, will come back, again will stay there. Will it happen? Then what
No,
is the J playing the role? There is a moment of inertia.
Yes,
That
sir.
won't
Yes,
allow
sir.
the pointer to come back.
Yes, sir.
See, you are running your two-wheeler, at 50 kilometer per hour. Stop your acceleration. Acceleration is made 0. If you make your acceleration 0, will you stop the vehicle without braking?
No, sir.
Are you getting my point? You're running your two-wheeler at some speed, then make the acceleration 0. Don't apply the brake. Acceleration alone is made 0. Acceleration made 0 doesn't mean the speed is 0. Are you getting?
Yes, sir.
Can you stop by making acceleration 0?
No, sir.
Leave the hand from the accelerator. Will the vehicle stop immediately?
No, sir.
Yes, it's running because of whom? All of you getting my
Uh,
point? It's running because
yes,
of
sir.
whom? Why it is
Already
running?
created.
You made the
Moment.
acceleration 0. Yes, it's a moment of inertia.
Yes, sir.
Yes, same thing happens here in the instrument
Yeah.
also.
Okay, sir.
Getting everyone?
Yes.
Okay, the pointer cannot deflect like your instantaneous current. You are expecting that it will deflect from 0 milliamps to 3.14, will come back to 0, it will stay in 0, again will go from 0 to 3.14. It won't happen. Okay,
Okay, sir.
understood?
Yes,
All of
sir.
you getting this point?
Yes, sir.
So that's an interesting aspect of wave in general rectifier type instruments. Okay, you see everyone?
Yes, sir.
Yes, sir.
Okay. So we'll have a simple problem before getting into the next one. The next one will be full wave rectified instrument. Yes, we can answer. So we did the verification also for our design. That's all. Yes, you need one extra element, that is diode, ideal diode. But the problem is, if it is a practical diode, there is a loss of voltage. Agree, everyone? Yes or no?
Yes, sir.
Then,
Point,
including that loss, you need to go for the calculation of R series. All of you getting? If it is a practical diode, you need to lose that 0.7 in the peak value. Okay, so because the peak is 10 into root 2 at full scale, instead of 10 root 2, there is a loss of 0.7 across the diode. That's approximate calculation only. So then actual current will be 10 root 2 minus 0.7 divided by R series plus IP will change if the diode is. Let me have one more slide so that we'll consider this practical aspect as well. Suppose if the diode is practical, assuming diode is given as practical with a forward drop of 0.7, then how to make the design? Design changes slightly. Again, it's the same instrument 0 to 10 volt. Now Vin is 10 volt RMS. So problem at full scale. Now I am interested to find out only the instantaneous peak current. That's a moving coil current. So it is going to be again something like this. I want to find the peak current. Tell me what's a peak current, IP. So to find IP, you need VP. What is VP? VP is 10 into root 2. So problem at theta equal to, at full scale, and that too at theta equal to pi by 2, I want to find only the peak current. So 10 root 2. But what's a forward drop across diode?
0.7.
0.7. Then tell me what is the rest of the voltage available to produce your peak current? This is 0.7. Lose 0.7 from 10 root 2. Tell me what is this point potential? Assuming it's a reference. 10 root 2 minus 0.7.
13.4421.
Already you made a design. We'll see what problem you're going to get because of this diode loss. If the diode is practical, having a 0.7 closer to 0.7. If it is less, things are better. Assuming it's a 0.7 loss. So what is the voltage? 10 root 2 minus 0.7. How much voltage?
13.4421, sir.
4421 volt. Now tell me what is the peak current. So this voltage is across this voltage. 13.4421 is this point potential. This is falling across your R series and R meter. So tell me what's a peak current? 13.4421 volt divided by total resistance. That is 4501.6 ohms. Correct? Yes. Tell me what's a peak current.
$2.986 milliamps. 2.986 milliamps.
2.986 milliamps. So tell me what's average current by pi.
0.95.
Next digit, Tanvasha.
04 milliamps.
Okay, 95 milliamps. So input is 10 volt RMS, but we are expecting the full scale deflection of the pointer, but pointer will deflect only to 0.95 milliamps. Who takes the credit? Who takes the credit for this problem? Forward drop off.
Diode.
0.7. 0.7. Forward drop of 0.7. Diode drop. Okay, won't allow the instrument to read full scale. So therefore, R series has to be reduced. If you reduce R series, it will increase the peak current. Then it is possible to make the design. So what's only change? Tell me what's the equation we had earlier? What is the equation we had earlier? Go with the equation. So R series plus RM is equal to earlier. What is that? VP by pi. Okay, that's a voltage, average voltage into IFST. It is something like V average divided by I average. So IFST. That's the equation. Hope you remember. Remember this?
Sir.
Yes, that's the equation. So now you don't get VP at this point. What do you get instead of VP? This is VP. Earlier diode is ideal, you got VP. Now you are not getting VP. What are you getting? VP minus. VP minus 0.7. That's all. That's a change. Yes, that's a change in the design. Yes, go for the new calculation. That's all. Calculate your R series. Lower your R series. That will take care. This is the fault. This is the fault now. Or problem. So correction. Remedy for this. Calculate the new one. So you know already VP minus 0.7. What is that? 13.4421 divided by pi into 1 milliamps. Do that. 13.4421 divided by pi into 1 milliamp. That's the resistance you need as a total. Tell me what's the total resistance now needed. Change in design when you consider diode drop.
Total resistance is 4287. 4278 point, sorry, sir. 4278.75.
4278.75
Yes, sir.
ohms. Lose 10 ohm. That's your R series.
4268.75.
That's all. That's a new design. Therefore, new R series should be 4268.75 ohms. All of you getting? All of you getting?
Yes, sir.
Now, if you calculate 13.4421 divided by this resistance, tell me what is 13.4421 divided by 4278.75? 13.4421, a small verification of itself. 13.4421, that is the voltage at this point, divided by this is modified. Instead of 4491.6, it is now chosen as 4268.75. Including this 10, it is 4 to 78.75. Now tell me what is this ratio? 13.4421 divided by 4 to 78.75 will give you the new peak current. Tell me what's a new peak current? Hope it is 3.14.
Yes, sir. 3.1.
Yes, sir.
That's intention. If the peak current is 3.14, now tell me what's average? That's instrument reading. 3.14 milliamps divided by what? Pi. What is the current
1
then?
milliamp, sir.
Yes, perfect.
Yes, sir.
So for the loss of voltage, you compensate the voltage, compensate this loss of voltage across the practical diode by lowering your R series. Okay, by lowering your R series. When diode drop is given, this is the equation you need to play with. When diode drop is given, that's the equation. Okay, all of you getting? All of you getting?
Yes, sir.
How to remember the equation now? No diode drop. Ideal diode. Then R series plus RM should be remembered as V average divided by IFST. Simplest equation. What is the V average? And you are playing with half-wave rectifier. What is the V average of half-wave rectified signal? Vp by pi. It becomes Vp by pi into IFST. All of you getting? Is he right?
Yes, sir.
Then diode drop is given. When diode drop is given, then it becomes R series plus RM is equal to your V average minus 0.7 divided by IFST. That's all. Then your V averages. Any mistake I'm committing? That's correct. Okay. Some mistake I committed here.
VP minus 0.7, sir.
VP minus. Okay. I committed some mistake here. It is VP minus 0.7. Yes, this is correct.
Yes, sir.
This is correct. This has to be corrected. Correct?
Yes, sir.
It has to be VP minus.
Points.
It's approximate only. Okay. These are all. This is approximate only because your instantaneous waveform will change actually because of diode drop. Okay. If no diode drop, this is your rectified signal. If there is a diode drop, the rectified signal will become something like this. It is no longer a pure sine wave. That's a problem, but still that's why it is approximate. This is VP and this is VP minus 0.7. All of you getting? Then divided by pi. VP minus 0.7 by pi is your average. All of you getting? Yes or no?
Yes, sir.
That's your average. Then by IFST. So therefore it becomes VP minus 0.7 by pi times IFST. Okay. Go by concept. Okay. So try to reduce remembering the equations. Getting everyone? Following right?
But these equations validate the peak value at theta is equal to pi by 2, no, sir?
No, it is not only a theta equal. This is the design, Nirmala.
Okay, sir.
We made the design actually to find the peak current only we played at pi by 2. Getting, Nirmala?
Okay, sir.
I just wanted to know the peak current going through the coil. Once I know the peak current, I know how to play with the average.
Okay, sir.
Correct? So to get the average quickly, we need to play with the peak current of the instantaneous waveform. Therefore, instead of taking Vp sin omega t as the input and going for the current as a Vp sin omega t divided by R series plus R pi, I'm taking the peak value. So setting the problem at full scale for the maximum current and that too at what? Pi by 2 to get the peak.
Okay, sir.
Okay, so problem set at pi by 2 to play with the peak information only. Getting everyone? All of you getting? Because with
Yes.
the peak voltage, you know the peak current. With the peak current, you make the design. Because once peak current is known for the off-wave rectified signal, what is the average current? IP by pi. So it's easy. Understood?
Yes, sir.
That's a point. Okay. Why we have to play at pi by 2 only. Okay. That means you should not conclude that this design is valid only at theta equal to pi by 2. It's everywhere, right?
Yes, sir.
Understood, Nirmala?
Yes, sir.
Okay. Yes. Calculations made at theta equal to pi by 2 to find the peak value of the current exciting the moving coil. With that, we can quickly go for the average. That's intention. Hope everyone is clear about this. Yes.
Yes, sir.
Then let me talk about a factor, a theoretical factor. Tell me, assuming diode is ideal, it's only when diode is ideal. What is a DC voltmeter sensitivity? Because now we have a AC voltmeter. We have built an AC voltmeter which is capable of reading RMS. What about our DC voltmeter sensitivity? Whenever we have a DC voltmeter, the DC voltmeter sensitivity referred by S ohm per ohm, that is equal to 1 by IFST. Correct? Yes or no?
Yes, sir.
Then whenever 0 to VFSD is given, we calculate the total meter resistance, including meter resistance as R series plus RM is equal to what? S ohm per volt into VFSD. That's how we calculate our total resistance. With that, we calculate quickly our R series. That's what we have done. We do theoretically in DC voltmeters design. Getting everyone? Yes or no?
Yes, sir.
Now we are doing off-wave rectifier based AC voltmeter. Off-wave rectifier based AC voltmeter. So this sensitivity, let me refer this as a DC sensitivity, DC voltmeter sensitivity, that is S ohm per volt, that is equal to 1 by IFSD. Here also we are using the instrument. Here also we have the IFSD. What is IFSD for the instrument? 1 milliamps. Now can you tell me what is the sensitivity of the AC voltmeter? Sensitivity of the AC voltmeter. SAC I'm talking about. So SAC is nothing but what? SAC is nothing but what? Similar to the DC sensitivity in DC voltmeter, if I know SAC directly, I can find out the total resistance. Yes or no?
Yes, sir.
So therefore, R total is equal to what? SAC into what? VFSD. This VFSD is the range of the AC instrument, but this VFSD in RMS, correct? This VFSD is in RMS. So that's a voltage number only here. So R total I can calculate quickly. If AC sensitivity of the AC voltmeter is given, I can quickly find the total resistance. That total resistance is still R series plus what? RM. Agree everyone? Yes or no?
Yes, sir.
Now tell me what is the AC sensitivity. So for that, directly I'll go with the data. Last example. What is our R total? Otherwise, I can say SAC is equal to SAC is equal to SAC is equal to R total in the AC instrument divided by VFSD. So VFSD is 10 volt RMS. To say it is AC. What is the R total we had for the last instrument? Because we made 0 to 10 volt instrument. What is the R total we had in the design? What is the R total we had? 4.5016 kilo ohm. All of you getting?
Yes, sir.
So then take that number. So it is 4.5016 kilo ohms. Tell me what's the number? 0.45 kilo ohm per volt approximately. Agree all of you? Agree with this?
Sir,
Yes, Rahul?
VFSD in terms of uh,
AC
To be
voltage.
measured voltage. Okay.
Yes, 0 to 10 volt RMS.
Okay. Okay.
Getting everyone?
Not the PMMC instrument.
No. What here? What is 0 to VFSD? DC voltage. Here, what is
Yes,
0
sir.
to VFSD? AC voltage. Because here it is a DC voltmeter. Here it is a AC
Yeah. Okay,
voltmeter.
sir. Okay, fine, sir. Okay.
All of you getting?
Sir.
Now, can you compare your AC voltmeter sensitivity with the DC voltmeter sensitivity? AC. What is the DC sensitivity here? DC. Because the instrument is same. What is the IFSD? 1 milliamps. Suppose with the meter moment of 1 milliamps, if you build a DC voltmeter, then what will be the sensitivity of the instrument? 1 by IFSD. 1 by 1 milliamps. What is that? What is that? 1 kilo ohm per volt will be the DC voltmeter sensitivity. Hope everyone is following this.
Yes, sir.
Hope it is visible to everyone. Right side, right corner.
Yes, sir.
Yes,
Yes,
sir.
sir.
SDC is 1 by IFSD, that is S ohm per volt, that becomes 1 kilo ohm. But unfortunately, when I use the same meter movement for AC voltmeter design, because it is built by using off-wave rectifier, it's not a constant current, it's a pulsating current. Because of that, sensitivity decreases to 0.45 kilo ohm per volt. Therefore, SAC by SDC, go for the calculation, it is 0.45 kilo ohm per volt. And this is 1 kilo ohm per volt. Therefore, the factor becomes 0.45 roughly. Therefore, the conclusion is SAC is always 0.45 times that of SDC. Therefore, SAC is 0.45 times by IFST. That's a conclusion. This is still S ohm per volt in AC voltmeters. All of you getting?
Yes, sir.
All of
Yes,
you
sir.
getting this? Yes or no?
Yes, sir.
That's when diode is? When diode is?
Ideal.
Ideal. Okay. Now we'll see how to exploit this data. Now I'm taking the same circuit once again. I'm going for a new design. I'm designing a 0 to 100 volt RMS AC voltmeter with a meter movement with a small change everything. It is 0 to 10 milliamps for a change with RM is equal to 100 ohms. The meter movement is changed. The PMMC is changed. The question is, what is the RSC needed? Assume diode is ideal. That's a design. Directly the question on R series. I want to design this. So find out the value of R series needed so that this circuit acts as a 0 to 100 volt RMS AC voltmeter. This is your AC voltmeter using rectifier basics. Yes, can you tell me quickly what is the answer? You need not to play with insert. The basic route is you have to go for the PMMC current, PMMC of T. And from this you need to find out the peak. Then you need to go for the average. Then you will get average is equal to IP by pi. This IP will be a function of VP by R series plus RM. Those things by pi. Otherwise you need to remember the equation. Then you need to find out R series plus R total. Then from this you need to find out R series. That's a route. Getting everyone? Yes or no? Yes or
Yes.
no? Now, forget everything. I'm giving you the basic movement. The basic movement is 0 to 10 milliamps RM. So I'm giving you a theoretical statement now. I'm building a 0 to 100 volt RMS AC instrument using a PMMC ammeter that is having full scale deflection current of 10 milliamps. That is having RM is equal to what? 100 ohms using off wave rectifier fundamental means what should be the series resistance needed for the design. That's how the question will go. Okay, they won't show the circuit also. That's how we need to make. Where to begin the problem? Begin with SAC. What is SAC? SAC is equal to what? 0.45 times that of what? SDC. Correct? What is SDC? So it is 0.45 times. What is SDC? 1 by IFSD. All of you getting? Find out SAC. What is that? 0.45 into what is 1 by IFSD? 1 by 10 milliamps. What do you get then? Yes, what's the number?
45
45 what?
ohms.
Ohm per
Ohm
volt.
per amps.
All of you getting?
Yes, sir.
Yes,
Then
sir.
tell me what is the R total needed for the AC voltmeter? For AC voltmeter, what is the R total needed? R total is R series plus RM. What is that? SAC into VFSD.
VFSD.
Yes, tell me what is R total needed? That is R total, or directly can say R series. That's a meter resistance. Meter resistance is different in AC voltmeter. That's a AC voltmeter total resistance. So R series plus RM is equal to what you get? SAC is 45 ohm per volt. It's approximate into VFSD. What is the VFSD? 100 volt RMS. Getting everyone? What is the number then? 4500 ohms. All of you getting? Yes.
Yes, sir.
Then tell me what is R series. Subtract RM. Getting everyone? Yes or no?
Yes, sir.
Following or not?
Yes, sir.
All of you getting this?
Yes, sir.
Deepthi following this?
Yes, sir.
Okay, yes. Then get back to the circuit. What is the R series? We have decided 4400 ohms.
4400.
Now verification can be done. Verify. Set 100 volt. Check whether it is at full scale or not. Full scale is 10 milliamps. Apply 100 volt. What is the peak value? What is the peak value? Assume the input is peak. What is the peak? 100 into root 2. So find out the peak current. Peak current through the instrument exciting the moving coil. 100 root 2 volt divided by total resistance. This is 100 ohm. 4500. 100 root 2 by 4500 ohm is the total. Tell me what's a peak current through the instrument.
Thirty-one point
31 point.
4 milliamps.
So that is your instantaneous waveform. Half wave rectified signal. This is the peak I'm talking about. Tell me what's average current. That's the reading of the instrument. Therefore, meter reads I average. What is that? IP by pi. That's the reading of the meter. What is that? Divided by pi. Happy everyone? Getting? All of you getting?
Yes, sir.
100 volt RMS should produce full scale deflection. Input is 100 volt RMS. Reading should be 10 milliamps. Okay, full scale 10 milliamps finally calibrated to read what? 100 volt RMS. Easy? Easy everyone?
Yes,
Yes
sir.
or no? Then you need not depend on this route. Clear?
Yes,
This is
sir.
the basic route. Okay, if there is any confusion in this, you can play with this route. Then that's the purpose of building AC sensitivity. AC sensitivity of the old meter. AC sensitivity of off wave rectifier instrument. Okay, getting everyone? Yes or no? We'll do this similarly for the full wave rectifier instrument. This completes, okay, in all aspect your off wave rectifier instrument. How to make a new design means you understood everything. Then you connected through the DC sensitivity of the DC voltmeter and AC sensitivity of the AC voltmeter. AC sensitivity of the voltmeter, the important point is always less than DC sensitivity. Yes, AC is always less than what? Yes, DC. So if you are building a DC voltmeter using PMMC, the sensitivity is higher, the meter resistance also higher. If you go for AC sensitivity, if you're using the same meter movement for the AC voltmeter, the AC sensitivity is less than the DC voltmeter sensitivity, therefore the meter resistance will be less. Therefore, if you make a 0 to 100 voltmeter, DC voltmeter, using that PMMC, the resistance will be higher. Whereas if you make a AC voltmeter, the resistance will be lower. Following everyone? Following everyone? Yes or no?
Yes.
Yes, sir.
Because of AC sensitivity and DC sensitivity are not identical, when AC sensitivity is less for the same meter movement, definitely the total meter resistance also less. Okay, so therefore we can't calculate or use the design procedure we used for DC voltmeter for AC voltmeter, because we have pulsating DC. There we have perfect DC. That's a difference. All of you getting? Yes or no?
Yes, sir.
Okay, yes. Yes, with this half wave rectifier instruments done comfortably. Yes, answer this problem. Some problem using a diode, that's all. Give me the answer. Ideal diode has been connected across a 10 ohm, 100 milliamps, center zero PMMC meter. Take that way. Maybe our Satish sir used ohm symbol, I guess, but somehow got misplaced as watts. Okay, everywhere. We'll correct it. That's a printing mistake. Yes, it is given clearly in the meter, adjacent to the meter, right? Understood? 10 ohm, 100 milliamps, center zero PMMC meter. The meter will read what? That's a question. What will be the reading of the meter? Excitation is AC. AC voltage. It is given in the form of Vp sine omega t. Use necessary information. Ideal diode? Yes, diode is ideal. Yes. Diode will conduct during positive of cycle or negative of cycle.
Positive of cycle, sir.
Yes, during positive of cycle, diode will conduct. If diode conducts, it is replaced by what?
Short, sir.
Then is there any current through the instrument?
No, sir.
No, sir.
No current through the instrument directly. That's why I said focus on current I of t. That is the current through the instrument. So focus on current through the instrument. That's easy. That will make the problem very easier. And no, since diode is on, there won't be any current through the instrument during positive off cycle. That is 0 to pi. No current through the instrument since diode is on. Okay, during positive off cycle, diode is on. Current I is equal to 0 through the instrument. All of you getting? Yes,
Yes, sir.
because diode is in forward bias. During negative off cycle, pi to 2 pi. During negative off cycle, diode is definitely in what? Reverse bias. During negative off cycle, diode will be in what? Reverse bias. Reverse bias means diode replaced by open circuit. Then what is your circuit? 990 and 10 ohm is your circuit. But this is negative, this is positive during negative off cycle. Therefore, the current will be this way. Getting everyone?
Yes, sir.
Then current is negative or positive through the instrument?
Negative, sir.
Can you allow it?
Yes, sir.
All
Center
of you,
zero.
can you allow this current? Yes, it's a center zero PMMC capable of reading negative also. Therefore, the current I of t is negative. Tell me what is the peak input voltage? 100. Input is not varying. It is constant. 100 volt peak. Across 100 volt peak. 1 minute. 100 volt peak. Across 1 kilo ohm. 990 plus 10. It is 1000 ohm. Will create a current of how much? That's a peak current. Negative peak current. How much? IP. 1 by 10? 1 by 10? 0.1. In milliamps? 100 milliamps. 100 milliamps. Negative current is going. So mark it this way. That's your current. All of you getting the point?
Yes, sir.
Yes or no? What is the current value?
Minus.
Minus 100 milliamps. That's what happens again during positive off cycle. Therefore, yes. Yes,
Okay.
Dhanvasha?
No,
What?
sir. I thought that
Positive.
100 is RMS. Okay, I got confused. It's correct.
This 100 is peak. I said VP sin omega t, right?
Yes, sir.
It's peak. Therefore, that is making this current. Therefore, what's average? Instead of a positive average, this will result in negative average. Therefore, I average is equal to the peak value by pi. What is the peak value? Minus 100 milliamps. So this is resulting in a negative average by pi. That's a current through the instrument. Average current through the instrument. Average of this waveform. That's all. IP by pi. What is IP? Minus 100. That's all. Yes. Minus
31.
31.8.
0.8 milliamps. Option. Hope he has given plus 31 also. Yes. Okay, plus 31 also there. We should not commit a mistake. Yes. Current is instantaneous current is very important. So during positive off cycle, current is not existing in the polarity marking. During negative off cycle, current is going from negative to positive. So it's a center zero PMMC, negative current is allowed. Okay, so take it. Okay, so that's an intentional play by the designer, and plot the current in the negative off cycle with the negative value, know the negative peak, and then it's like a off average only. So no conduction during positive off cycle, conduction during negative off cycle. With the negative value, go for the negative average. Okay, like this is like a negative off wave, something like this. Negative off wave. What will be the average? Peak by pi. This is your negative peak. So minus IP. So therefore I average will be minus IP by pi. IP you know already 100 milliamps. With that you can complete. Is it right?
Sir, since here the position of the diode is changed, we are getting negative.
Yes.
Okay, sir.
For the given circuit, what is the answer? If you reverse the diode, your answer is different.
Yes, sir.
If you reverse the diode, answer will become plus 31.8. Understood?
Yes, sir.
Because diode will become off during positive off cycle, therefore current will go through the instrument during positive off cycle. So then your waveform will change. Current waveform through the PMMC will change. So
Sir?
whenever a PMMC with the AC, always focus on current through the moving coil of the PMMC. Getting everyone?
Yes.
Then go for the average.
Sir?
Yes, Monopriya.
Yes, sir. When the diode is on, how the current I is 0, sir? I continue.
Because diode is replaced by a short circuit, right? What is the voltage across on diode? 0 volt. And take this as a reference. This is 0. What is the top? 0. Then what is the voltage across instrument? 0. Will there be any current across 10 ohm?
No, sir. Okay.
Understood?
Yes, sir.
You have two elements in parallel. One is a perfect short. Another one is a 10 ohm. So what is the net equivalent? 0 only. Where the current goes? Only through the short.
Diode. Okay, sir.
Okay, through the diode.
So in this, what it represents, sir? 31.8 milliamps representing 100 volts, sir. Peak voltage.
No, here it is simple problem. That's all. Okay, so input is given. It's a constant signal given, Monopriya.
Okay, sir.
So for the given excitation, what is the current through average current through the instrument? That's all.
Okay, sir.
Okay, he has made the design already. Okay, some
Okay, sir.
design he made. He is asking us to find the deflection of the instrument. That's all. How much current will be going through the instrument? That's all. So what is the instrument PMMC? What is the current? It will show only average current. So what is our focus? Get the instantaneous PMMC current, go for the average. That's all.
Okay, sir.
All of you getting this point? Yes.
Yes.
Yes, sir.
Okay. Next one. Okay. Instead of half wave, let us go for the full wave. So let us increase the average. In fact, the average will get doubled, correct? Yes or no?
Yes, sir.
When the average get double, average voltage increases for the same input range because of full wave rectification. Therefore, the sensitivity of the AC voltmeter actually will increase. Okay, we'll see that. Okay, so the sensitivity for full wave is different. What is the sensitivity given earlier? It is only for the off wave. That's a point. This is only for the off wave. Whatever the sensitivity we discussed, only for the off wave. Off wave sensitivity is this. Okay. Okay, this is a off wave already given, right? Only for the off wave rectifier. Full wave rectifier, the calculation will be little different. You will get a better sensitivity because you get higher voltage. You have to produce the same peak current. Therefore, the burden, okay, so is less. Okay, therefore, you need to have a increase in R series. Okay, same setup. Let us begin with this setup. So directly we are beginning with the bridge rectifier. Because what is the another rectifier we have is a center tapped transformer rectifier. So we prefer this. Okay, don't demand a center tapped rectifier. So that discussion we made an analog. Okay, so check that once again. Those who didn't attend analog, you'll be covering that. Okay, let me directly go with the full wave bridge rectifier based PMMC instrument. Shortly, full wave rectifier, full wave bridge rectifier instrument. Okay. So there's a V in of T. Polarity marking is very important here in this. Polarity marking is very important because current should go this way. If you change the polarity, then current will be reverse, then instrument won't deflect. Therefore, off wave rectifier instrument, you still have the polarity marking for the AC. Is this clear, everyone? Yes or no?
Yes, sir.
Okay, but whereas in full wave polarity marking not needed, so you can connect your source anyway. Okay, so because this is diode D1, this is diode D2. So diode D1 and D2 will take care of conduction during positive off cycle, and D3 and D4 will take care of conduction during negative off cycle. We'll see that. Again, it is 0 to VFST, that's AC voltage to be measured. So now I'm connecting a R series in series with the PMC. That's a setup. We use it for DC voltmeter also. Along with the setup, I consider the bridge rectifier. That's all. So the bridge rectifier will convert. What the bridge rectifier will do, will sense this V in of T, will convert this into what? A pulsating full wave rectifier DC. That will be exciting effectively your PMMC and R series. This is exciting your R series and what? PMMC. So with this, we are going to play. Getting everyone? This will be the excitation here. Getting all of you?
Yes.
Okay, so that's effective equivalent. We'll see what is happening in this. Let me begin with the positive off cycle analysis. So during positive off cycle, we'll see what happens. Positive off cycle, again, I play at theta equal to pi by 2. Positive off cycle analysis at theta equal to pi by 2. This is VP at pi by 2. So therefore, take this as a reference. So this is VP. This is VP. And D1 is on. D2 also turns on. Why? Okay, because positive off cycle means current will be this way. Because this is higher potential, this is lower potential, current will be this way. And who will support the direction? D1 will support. Current cannot enter this way, immediately make the current 0. That's a path of current flow. So current will be going this way. Then through the instrument this way, because this current will become 0. This diode won't support. So then going through the instrument, and then that's a path for the current. That's how it is going. Getting everyone?
Yes,
So
sir.
D1 is on, and then what? D2 is on, whereas D3 is off and D4 is off. Okay, that's your path. So it is making plus and minus. So PMC is having polarity marking. That's the direction of the current I of T, instantaneous current through the PMC during positive off cycle. Same way during negative off cycle. So apply a negative cycle. So this is minus and this is plus. So take this as a reference and take this as a VP. That's easy for the analysis. So this is VP. This is VP means how the current will be. So from here to here will be the current. This is a current path. Therefore, who will support? This won't support. This current is 0. This will support. That's your D3 and this is your D4. So the current is going to be this way. So then again, it won't support the direction. Current is 0. Then that's a path for the current flow. Then that's how the current is coming back. What of the current going I of t? That's a current coming back here. Getting everyone? Who are in on condition? D3 is on, D4 is on. Is it clear?
Yes.
And current direction is unidirectional or bidirectional? Earlier the current is right to left. Earlier. Now also the current is what? Earlier this is the current direction. Okay. The current direction through the R series and PMMC doesn't change. Current direction through the R series and PMMC. In fact, forget about R series. R series can be connected anywhere. Okay, so we are focusing on, because resistance, current through the resistance can be bidirectional, but not current through the PMMC. PMMC should be what? Current through PMMC should be what? Unidirectional. Okay, it's because it's having the polarity. So this is what happening during positive off cycle. Positive off cycle current is right to left. In negative off cycle also current is right to left. Therefore, the PMC is going to have the current unidirectionally, like your full wave rectified signal. That's a current through the PMMC. All of you getting? This is 0 to pi and pi to 2 pi also current is unidirectional. Easy? That's the purpose of going for a full wave bridge rectifier. Understood? Understood?
Yes, sir.
Yes. So during
Yes,
off
sir.
wave rectifier instrument, in off wave rectifier instrument, no current existing through the PMMC during negative off cycle. Correct? No current during negative off cycle. Therefore, it is resulting in lesser average, lesser deflection. Whereas in full wave rectifier instrument, through the PMMC, we get the signal during positive off cycle as well as negative off cycle, but it's a unidirectional current, positive current existing in positive off cycle of input as well as negative off cycle of input. Therefore, okay, it will create a higher average. Therefore, you can go for higher resistance, okay, so that you can reduce your current. What is the average here? 2 IP by pi. What is the average here? IP by pi. Understood? Therefore, it will deflect more if you allow more current. Therefore, let us reduce the current by increasing R series. That's what we are going to do. Getting everyone? Following this?
Yes.
Sir.
The schematic may be a little different. It may be like this also. Never get surprised or confused by seeing the schematic. This one. It can be like this also. You see what difference between the two? I have connected R series in series with the instrument, but anyway R series always there in the circuit, correct? Always R series there in the circuit irrespective of the direction of the current. So I can connect R series like this also. Okay, getting all of you. During positive off cycle,
Yes.
the current will be, during positive off cycle, the current will be this way. Getting all of you? That's a positive off cycle current.
Yes.
Agree? Negative off cycle, the current is this way. Correct? Yes or no?
Yes.
But current through the R series can be bidirectional, not an issue. Understood? But irrespective of that, what is the total resistance your circuit sees? Irrespective of the current direction, the total resistance in the circuit is R series plus Rm. Understood? Yes or no? All of you getting? Yes or no? Who limits the current in the circuit? Assuming diodes are ideal, there is no drop across them, there is no resistance. Okay, when you go in this path, diode is not taking any drop and drop across Rm and then drop across R series. So therefore the total is, effectively they are in series. So they are responsible to limit the current. Therefore R total is depending on R series plus Rm. So this is giving you the easy step because this is R series and this is what? Rm, and they are in what? Simply in series. So here diode drop is 0. Therefore, this is your VP and this is on condition, this potential is 0, this is 0. Tell me where the entire voltage falls. Entire voltage, this is VP and this is what? 0. Tell me where the entire voltage falls across R series and RM. Agree everyone? Then tell me what's a peak current then? The peak current is going to be VP divided by what? R series plus RM. So automatically, who is your total resistance? R series plus RM. All of you getting this? Yes or no? Following or not?
Yes, sir.
Yes, now let us make the design. Understood everyone? So design for 0 to 100 volt RMS. I want to build, better let me take a number different, a little different. I'm building a 0 to 50 volt RMS instrument. The question is, what is your R series? We need to find, that's a design. So set the problem at full scale deflection. Full scale deflection means what? Your input should be, we are designing 0 to 50 volt RMS full wave rectifier based PMMC instrument. Now set the problem at full scale. What's input voltage applied? AC voltage applied.
50 volt.
Apply the AC voltage. What is that? 50 volt RMS. 50 volt RMS you take. Okay? Getting everyone?
Yes.
Yes, sir.
Tell me what will be the peak current. Now let me play for the positive of cycle. 50 volt RMS I am playing. What is the positive of cycle? Let me play for the positive of cycle. Positive of cycle, what's the peak? 50 into root 2 volts. Correct? At theta equal to pi by 2. So that's a peak voltage. Let me take this as a reference. This is plus minus. Therefore, it is VP. So this is 50 into root 2. That's a voltage. And this is 0 volt. Therefore, the current will be through this. Okay. So tell me what's a current I of t for this period through the PMMC. Current through the PMMC is this. Tell me what's a peak. The peak is going to be 50 root 2 divided by what? R series plus RM. That's a peak current. Getting everyone? That's your IP. Following all of you? Yes or
Yes,
no?
sir.
Since it is full wave rectified, it is going to make the same representation during negative off cycle as well from pi to 2 pi. Therefore, what's I average? That's a one deflecting the instrument. I average is going to be 2 IP by what? Pi. Getting all of you?
Yes.
So by the time I give 50 volt as a full scale, my current should be equal to what? Full scale current. Getting everyone? What is the full scale current?
1 million.
1 milliamps. Therefore, 50 volt RMS has to create 1 milliamps. Little different design. So therefore, 2 IP by pi should be equal to what? 1 milliamps. Then complete the design. Complete the design. So 2 by pi IP is equal to, yes, 1 milliamps. What is IP? 2 by pi. What is IP? IP is already given
50 root 2 pi.
by R series plus
R
RM.
series plus R.
So therefore 2 times IP is 50 root 2 by R series plus RM. That's 2 times IP by pi. That should be equal to 1 milliamps. So from this, tell me what is R series plus RM. Calculate R series plus RM is equal to 100 root 2 divided by pi into 1 milliamps. That's all. Getting everyone? 2 into 50 root 2 becomes 100 root 2 divided by pi. So then take R series plus RM to the right side, 1 milliamps to the left side. Yes, tell me what's the total now. R series plus RM is equal to how much?
What in terms of ohms, sir?
Yes. 100
What
root 2
is
is a volt.
yes, sir.
150 root 2 is a volt. 100 root 2 is a volt. Volt by amps. 100 by root 2
Okay.
kilo ohms total. 100
45
root 2 by
kilo.
pi kilo ohms. Tell me what is the number?
45.015 kilo ohms.
015 kilo
8
ohms.
kilo ohms.
Okay, 8 kilo ohms. We'll get the same numbers once again. Tell me what is our series? Lose 100 ohm. Sorry, 10 ohm. 10. What is the value taken we have earlier? A different design or same design? Okay, same instrument. Okay, 10 ohm. Lose 10 ohm. Lose 10 ohm.
45.
45.0148 kilo ohm you will get. 10 ohm you have to lose. 15.8. So 15.8 means that is 005.
Yes,
Yes.
sir.
Yes, sir.
0058.
0058.
Okay, 0058 kilo ohms. All of you getting? That's how we can make a design if it is full wave. Okay, so our series chosen. Our series is how much? 45.0058
58 kilo ohms.
kilo ohms. This is 10 ohms. Now verify at some other potential. Verify at some other potential. So 50 volt making 1 milliamps deflection means you go for any voltage between 0 to 50. You give me a number between 0 to 50. What is your expectation? We'll see what we are achieving finally. Yes, that's a verification. Verify your design. Yes, give me any voltage. 50 makes 1 milliamps. Give me a number between 0 to 50. Anyone? Yes, Deepthi, you can give any number.
26.
26 volt. Yes. What is your expected current? 1 milliamps for
0.26.
50 means then 26 should produce what current?
So
26 by
0.52.
50 milliamps. How much it is?
0.52.
52 milliamps is the expected current. What is this current? That should be the average deflection current of the pointer, correct? So therefore the meter current should be equal to, so sometimes I will say meter. Sometimes electrical students, you will be using IM in the place of IP. Apply caution. Because in some other subjects, maybe in electric circuit or in power system or in machines, okay, when you play with AC machines, you will represent the current as IM sin omega t. Understand?
Peak value we represent.
Okay, or VM sin omega t. Apply caution. Okay, this IM will be here representing meter current. That meter current represents only what? Average. So I'm using here as a peak. Okay, whenever I say maximum, that is a peak I'm using because IM means I refer meter current. Okay, therefore avoid this conflict. Okay, understood?
Yes,
If it
sir.
is instrument, use IM as a meter current
Yes, sir.
and IP as a peak value. So that's why I have the habit of playing with VP IP instead of VM IM. Understood? VM here refers voltmeter voltage, IM refers ammeter current. Understood? Yes. Now tell me what is the IM? That's the average. I average should be equal to 0.52. Now you are applying 26 volt RMS as the input. 26 volt RMS means what's a peak voltage? The goal is I want to find the peak current, IP. What is the peak voltage? 26 into root 2. All of you getting? That's a peak voltage. Assuming you are applying, okay, at problem is at theta equal to pi by 2. At theta equal to pi by 2, this is positive, this is negative. Okay, so that this is VP. So that VP is equal to what? 26 into root 2. So now this R series and 10 ohm only in series. And this is the path of your current. Oh, tell me what is that peak current going through the instrument. I'm talking about the peak current going through the instrument. Peak current going through the instrument at theta equal to pi by 2. The same current will exist at theta equal to what? At theta equal to 3 pi by 2 but in opposite direction, but through the PMC it is the same direction current. Understood? So this is at pi by 2 as well as at 3 pi by 2 you will get the same current, but the overall current rotation, sorry, the direction is different, but current through the PMC still remains same direction. That's a peak current you are getting at pi by 2 or 3 pi by 2. At 3 pi by 2 this will become minus. Okay, this is 26 root 2. Otherwise, you can take this is 0 and this is 26 root 2. You will get the same amount of current through the instrument. So, what is the peak? Peak current. So, this is at pi by 2 as well as at 3 pi by 2. That's a peak current through the instrument. What is the peak current? Peak voltage divided by total resistance R series plus Rm. So what is the peak voltage? 26 into root 2 volts. And total resistance we already know R series plus Rm. How much? 45.0158 kilo ohms. 45 or 46? 45. So 45.0158 kilo ohms. Tell me what's a peak current you're getting?
0.8168 milliamps.
0.8168 milliamps.
8168.
Is this full wave rectified signal or half wave rectified signal? It's looking like current through the PMC looking like half wave signal or full wave rectified signal.
Full wave, sir.
Then what's average?
2
2
IP
into
by
IP by
pi.
5.
Then yes. Tell me what's the number.
0.52, sir.
Getting all of you?
Yes, sir.
Yes, sir.
Easy? Easy, right?
Yes, sir.
That's a way to verify your design. Easy, Deepti?
Yes, sir.
Okay, so we are covering many topics. On the way, we are covering rectifiers, little bit of analog circuits, okay, instruments also. Understood? Yes, the full wave rectifier
Yes, sir.
instruments.
Yes, yes.
Tell me what is the total resistance now? This part already we discussed. For half wave, we'll do it for the full wave. Okay, so the schematic diagram can be like this also. It is the same. Now tell me what is SAC. SDC, you know. What is that? 1 by IFSD.
EFSC.
Now I'm using the same instrument. Tell me what is SDC? What is the instrument used? 1 milliamps. So what is 1 by 1 milliamps? 1 by 1 milliamps. 1 by 1 milliamps is 1 kilo ohm per volt. That's a DC sensitivity. Ohm per volt sensitivity. Unit confirms what it is. Then what is AC sensitivity? R total divided by your VFSD. Directly go for that. It is yes. Ohm per volt. It is AC sensitivity. Yes. What is the R total we have? 45.0158 kilo ohm. 45.0158 kilo ohm. I'm going with the number. I'm not theoretically proving it, practically proving it. Okay. So VFSD. In this case, what is the VFSD? In our case, what is the VFSD we took? What is the VFSD we took?
50.
50 volt
50 volt
RMS.
RMS.
Then 50 volt RMS. That's all. It is volt. It is here volt RMS. Yes. Tell me what is SAC now?
0.9003.
0.9, sir.
00?
3
Please.
3.
Yes, sir.
Okay. Otherwise, shortly.
0.9.
0.9. What?
Kilo ohm per.
Kilo ohm per volt. What about DC sensitivity?
1 kilo ohm per volt.
Then what's the connection between them? SAC by SDC. Kilo ohm per volt RMS. It is kilo ohm per volt DC. What is the resultant? 0.9. Getting? From this, what's the conclusion? SAC is 0.9 times that of SDC if the instrument is full wave rectified instrument. Understood? All of you getting?
Yes, sir.
Yes, sir.
It is double that of off wave sensitivity. What is off wave?
0.45 times.
0.45. That's what we need to remember finally. So with this, rectifier instruments getting concluded. Off wave rectifier, that's a final hint for the design. SAC is 0.45 times SDC, where SDC is 1 by IFSD of the basic meter movement with which we are designing off wave rectifier instrument. If you are designing a full wave rectifier instrument, SAC is equal to 0.9 times, it's approximate, that of SDC. Again, SDC refers 1 by IFSD. That's how you can make the design. So here, once SAC is known, R total, that is equal to R series plus RM is equal to what? SAC into VFSD. That VFSD is in what? RMS. Getting all of you? Then you can go for this. Then from this you can find out R series. But this is only when
Diode is
diodes are ideal. If practical diode given, no, we can't use expression. Whatever the R series you are calculating will be less than this number because you are losing a potential. To compensate for that, you need to lose little resistance so that you can increase the current. That's a plan. Okay, find out this resistance. If only one option is having a resistance less than this, you can freeze it. You need not to go for a new calculations. All of you getting? Diodes are ideal. You can follow this. If practical diodes, yes. Okay, you have to compromise a little bit of resistance. Understood, everyone?
Yes, sir.
Yes, sir.
Anyone having doubts? This we have done already.
Then here for that we subtracted minus 0.7 no sir for practical. Here
Yes,
minus
from VP you need to lose minus 0.7.
here
Then we
double
have to do the
times.
same way.
Here 2 times 0.7 we should lose. No, sir.
Yes, 2 times 0.7 we need to lose. Because 2 diodes, right?
Yes sir.
Yes, definitely we need to lose 2 times. Getting Dhanvasha?
Yes sir. Getting.
So the moment something is different, start from the scratch, that route is also readily available. Okay. You try this problem. You have to decide a 0 to 20 volt RMS AC voltmeter. I'm giving you a PMMC of 0 to 10 milliamps with RM is equal to 100 ohms. That's given. You can also perceive like this. Easy, right? This perception is very easy, right?
yes, sir.
Yes. Easy, everyone. Sorry. Okay, full wave rectifier. What is the output? Easy.
Positive. Yes, sir.
Yes, that's a way. Okay, 0 to 20 volt RMS. You need to calculate R series for this design. That's all. It is plus minus. This is by using the bridge rectifier.
Diodes ideal or not, sir?
Yes, diodes are ideal.
Okay, sir.
Ideal diodes. Find R series alone. Try this later, not now. Try this later. Okay. That's your practice or example problem. Okay, so finally convince with your design. Do the verification at any other potential between 0 to 10 volt. Maybe try it at off scale deflection. Okay, so 20 volt RMS makes 10 milliamps. Deflection means 10 volt should make what? 5 milliamp deflection. Getting Rahul? Yes.
Yes, sir.
So verify yourself. That's why whenever you make a design, always do the verification also. So the important point about rectifier instruments results in very uniform deflection because still we use PMMC. So we use rectifier as an interface. If it is off-wave rectifier, we get less voltage, so less resistance for the meter. That's why the sensitivity is less in off-wave rectifier, because yes, AC is less means meter resistance also less. If SAC is more, meter resistance also more. So we get almost double the resistance in case of full wave then you are off wave. But anyway, the double the resistance means we talk about the total resistance only getting doubled, but you have to discard your meter resistance from the R series, R series plus RM expression. R series won't get doubled because only R total will get doubled because sensitivity getting doubled comparing to off wave to full wave. R total will get doubled, but the doubled value subtract RM from that, you will get R series. Approximately we can say if RM is negligible, R series also almost getting doubled, we can say, when you transfer your design from half wave to full wave. Is this clear? Understood?
Yes, sir.
Yes, sir.
So when you consider diode drops, you will be losing 1.4. Accordingly, you need to have a higher voltage. Okay, it's considered if it is given. Okay, practical diodes considered that. Then a problem which happened in gate 2003 as well as 2006 without any change in data, it happened. Okay, they made copy paste from electrical paper to instrumentation, 2 marks. You can check it by downloading the original paper. Yes, answer this problem quickly. You got all the fundamentals. It's your call. Route is completely yours. Play practically or play theoretically. All parameters are given. At least now you can play theoretically and complete the problem instantly. What is given? An AC voltmeter uses the circuit shown below, where the PMC meter has an internal resistance of 100 ohms and requires a DC current of 1 milliamps for full scale deflection. What is given? IFSD given, RM is given. So this is your meter resistance and this is your full scale deflecting current of your PMMC with which the rectifier instrument is designed. He said AC voltmeter. Okay, AC voltmeter, yes, using PMMC. Assuming the diodes to be ideal, the value of RS, what is RS? R series only. That's your R series. To obtain full scale deflection with 100 volt AC RMS applied to the input terminal would be. That's all. So he's applying 100 volt RMS. So that is treated as a full scale deflection voltage. And the meter current, that is your average current, that should be equal to the full scale deflection current. What is that? 1 milliamps. Find out your R series.
C option.
Option C, 89.9. What is the root, Rahul?
Sensitivity of it.
Yes. SAC is equal to 0.9 times that of SDC. What is that? 0.9 into, what is SDC? 1 by 1 milliamps, 1 by IFSD. Then what do you get? 0.9 kilo ohm per volt. All of you getting?
Yes, sir.
Then what is R total then? R total is equal to SAC into VFSD.
PFST.
Then tell me what you need. SAC is 0.9 kilo ohm per volt into VFSD. What is VFSD?
100 volt
100 volt. Then what do you get then? 90.
90 kilo ohms.
Then what is your R total?
RSC
Series
plus RM.
plus RM. Then,
Yes, sir.
then what's only unknown?
RSC
RSC, yes, R series. So 90 kilo ohm
minus
minus your meter resistance. What is the meter resistance?
0.1 K.
100.1 K. Answer is?
89.9 kilo.
That's all. Understood?
Yes, sir.
Yes,
Easy,
sir.
right? Imagine without AC sensitivity route, okay, how much time the problem will take. Understood?
Yes, sir.
Which route is better?
Sensitivity.
Sensitivity route is better. Yes. Of a rectifier, it is 0.9 times SDC. Sorry, 0.4 times SDC. Full wave rectifier, 0.9 times SDC. This is what expected. That's a final understanding needed on rectifier instruments. Only two expressions you need to remember: SAC and SDC. They will work only when the diodes are
ID.
only when the diodes are ideal.
Ideal.
Then we can't use this route when diodes are non-ideal. Go by that fundamental route. Understood?
Yes,
There
sir.
you set the problem at full scale. You set, but for the peak voltage you set the problem. Get the peak current. Okay, after losing diode drops, get the peak current, and approximately with that peak current, do 2 IP by pi. With that, you create full scale deflection. Accordingly, calculate your R series. That's very practical. Okay, you can't use the sensitivity route when diodes are non-ideal. Okay, understood?
Yes, sir.
Yes, sir.
That's a point. Okay, so with this, passive rectifier designs are over. So we'll do active rectifier designs using op-amp. We'll see the electronic rectifier instruments, okay, in the next session. Okay, yes, electronic rectifier based instruments, identical to this, little different. Okay, so with that, rectifier based instruments will be over. So any doubts till now? Any doubts till now? today's session?
No, sir.
Okay then. Take this one for your practice. These are the practice problems. Anyway, it will be there in your slides. Take the snapshot of this for the covered portion. Already we covered this. Take the snapshot and try them. Problem number 1 taken.
Yes, sir.
Yes, sir.
Problem number 2
Yes, sir.
taken, Rahul.
Yes, sir.
This we will do later. Problem number 3.
Yes.
So instead of watt, you make it ohms. Okay, that's a mistake. Okay,
Okay.
sensitivity is given. Okay, let me correct it. Kilo ohm
Ohms.
per volt. A rectified type PMMC voltmeter has a sensitivity of 20 kilo ohm per volt. Okay, so yes. And then here you take all kilo ohms.
So for ammeter, it will be kilo ohms per volt only, right?
Kilo
So for PMC ammeter, yes, sir.
PMC ammeter.
Yes, sir.
No, PMC ammeter, we never say the sensitivity in ohm per volt, Rahul.
Okay, sir.
Voltmeter only the sensitivity coming into play. Understood?
Okay, sir.
Yes, take the snapshot, everyone. Yes, these are the interesting problems. Try them. One,
Okay.
this one I will give later after the electronic rectifier instrument problems later. It's a bridge rectifier. In the feedback, we'll see all those things. You'll answer the problem after the next topic. Okay, so this is the second problem. This is the first problem. 1, 2, and this is 3. Okay, try them. Any doubts you have? Okay, so we can discuss in the next session. Okay, fine.
Yes, sir.
So next, because here the meter resistance is not great, again you will suffer because of the meter resistance. We want a voltmeter always to have what? Infinite resistance. If it is a voltmeter, always we need infinite resistance. So to get infinite resistance, once again we need to go for electronic. So it's a voltmeter. So you should have still infinite resistance. Yes, we'll see. This difference amplifier will make that infinity resistance. We'll see how we are going to design or understand the remaining things of electronic rectifier based instruments. We'll see that in the next session. So thank you everyone. So have your lunch. We'll meet at 3 today. So I'll go till 5. Remind me at 5 and schedule the signals from 5:30. I'll inform sir accordingly.
Okay, sir.
Okay, yesterday I have seen the video. So sir wanted to have at 5:30. So I'll close the session by 5 exactly. Okay.
Okay, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Thank you everyone.
Thank you, sir.
Sir.
Thank you, sir.
Thank you, sir.